So they were gonna, yeah, I'll have like these litter and then burn that off. I was gonna press and then I get back to this clear from straight eyes.
All right,
Yeah.
let's get started. I would love to finish the calculations and start chromatography. Just a reminder, I won't be here on Monday, but you still have class. All right, so, but Gary right next he's a treat. Ray can teach still. But Gary will cover gas chromatography. He spent his entire career, almost as many years as my age, on GC. So nobody can teach this better. So you're gonna enjoy him. He's such a treat, funny guy. And I want to get a little bit of that introduction to chromatography going so that you can engage with Gary on Monday. Okay, but I know I rushed through the dilution exercise. I'm going to go through it again with you. And if you have your sheet, please take it out and let's finish the calculations on your sheet. Make sure you write your name and then give it to either Andresa or Gray before you leave. And then I will post the version of these slides with the key, okay? So that you have all of that. All right, so this was, let me walk you through from the beginning. So it's a dilution problem. So we need to prepare standards at different concentration. Let's work with the first standard, which is 0.1 milligram per ml. And my starting solution, stock solution, is 16%. And what we did last time is we converted that to the same units. So we said 16% is in grams per 100 milliliter. Then we found we turned it into 16. Is that correct? Milligram per 1 mil, or what was the value for that one? No, 160. Sorry. Do we all know how we came to that? How we went from 16% to this? Are we all good with that? You can tell me. I'm happy to explain. Didn't say anything. I'm assuming you all good. All right. Then we said, okay, we need to prepare our first standard. If we use the equilibrium equation, then the standard that I want to get is 0.1 milligram per 1 ml, and I want to prepare 2 milliliters. And then my concentrated solution, standard solution, is 60 milligrams per ml. And then I want to know how much I need of that stock solution to prepare 2 ml of 0.0. Okay. Then we determine that it's such a teeny tiny amount. Remember that? And then even if we convert to microliters, go 1, 2, 3, because 1 milliliter is 1,000 microliters, then it's 1.25 microliter. That is so small. We don't have a pipette that can accurately dispense this much amount. So we said, okay, let's dilute. And then that's where I lost. Right? Okay. So if I want to comfortably pipette a volume, I don't want 1.25 microliter. I don't want 12.5 microliter. I don't want any 0.5 microliter. So we said maybe comfortably we can pipette 125 microliter. So I'll walk you through how we got all these calculations in a more simple manner. So let's say I want to take 125 microliter from a stock solution. Now I'm going to solve for what concentration should my stock solution be if I want to take 125 microliter to prepare a 0.1 milligram per ml of 2 milliliter solution. Okay, so now I just solve for this to see what should the concentration be of my starting stock solution. So if I do the math, it will come up as 1.6 milligram per ml. Correct? Are we following?
Yes. So if the 125 microliters is still microliters, what, do we have to switch to 2 milliliters to milliliters to do this?
Absolutely. Thank you. Yes. Wonderful. I was gonna do that in the next step. Or I didn't. I thought I would. But thank you for pointing that out. We definitely want to unify our units, and thank you. I missed that part. Yes, Ali.
If you know that you have to change it to, 100 microliters,
125.
yeah, 125. Could you just put it as milliliters instead, so you just keep them?
Point one.
0.125.
You could, yes.
Okay.
You could, either way is fine. Yeah. When it becomes a fraction of a milliliter, you will see that you will have a pipettes that are like 200 microliter pipettes, so you dial 125, so it's easier to remember it that way. You won't see 0.125 on that pipette.
Right.
But you can definitely do the math in milliliters. All right, so we're following up to here. So I need to dilute my original stock so that it is now 1.6 milligram per ml. And since I'm using very small amount, I'm gonna say I just want to prepare 10 ml of a stock solution. You don't need to prepare 100 ml. You could prepare 1 ml, but it would be too small. So let's say I'm gonna prepare a diluted stock solution 10 ml. So now you can still apply this equation. So I want to prepare 10 ml of my stock solution, which is now milligram per milliliter. So I need to prepare 10 ml from this diluted solution using the original concentrated solution. And now, what do I need in milliliter? If you solve for X ml, it will be that 0.1 ml we talked about, which is 100 microliters. So I would take 100 microliters plus 900 microliters of water. Oh, 9 and 900 microliters of water, because you want 10 ml. Then you will get your 10 ml. Is that okay so far? You following better than last time? Simplifying it. So last time I was trying to rush and told you, oh, so this is 100 times less. So you just need to dilute 100 times. But if you didn't catch how that came about, you can do all of that in a very simple, always applying the equilibrium. Okay. All right, now I diluted the sample. Then for 0.1 milligram per ml, I know I can take now 125 microliter. Now for the rest, you do the same, 0.2. So if I 1.2, I already have my diluted stock solution. So how much of that, let's just say in microliter, I need to prepare 0.2 milligrams per ml, and then 2000 microliters, which is equivalent to 2 milliliters. And then you solve for X, and in this case, X is 250 microliters. And then you do the same for 0.3 and 0.5. Okay. So in this case, you take 250 microliters and add to it the difference, which is 175 microliters of water to get to 2000 microliters. All right. Would you like me to say you anything or repeat anything? Well, all right. All right, give you a moment to write all this down. And then I'll post this with the answers. But if you have those equations written down, you can just follow it that way if it's simpler for you. Okay. Good. Questions? Okay. All right. So the last bit of calculation we're going to work on is your favorite of them all. Grace agree. Preparing buffers. Okay, you will also prepare a buffer next week in lab. So we're going to talk about how do we prepare a buffer with the given that we have. And there are a couple of ways we can go about it. So you can choose one way that is easier for your brains to understand. Everybody, I like one way, somebody else likes another way. Everybody is wired differently. So I'm going to show you two ways. Okay. So just as a reminder, buffers are made up of a dilute acid and its conjugate base. So dilute acids usually are organic acids. The conjugate base is really the salt of that acid. When you don't have a proton anymore, and then you have, let's say, a sodium ion instead of a proton ion, then it becomes the conjugate base. All right, if they are present together, then you have a buffer. And what it means is that buffer is used to buffer the pH of your reaction. So in your reaction, you want to maintain a specific pH, especially when it's enzymatic reaction, for example. So that's why buffers are meant to use weak acids and weak bases. So basically, they can pick up a proton and then give out a proton just to keep that buffer stable. Okay, you know pKa, right? You've heard about it somewhere in the distant past. So anybody remembers what it means? Or by looking at this Henderson-Hasselbalch equation, there are two guys, or I don't know, two people, I'm not sure of the guys. Henderson-Hasselbalch equation has a pH equal pKa plus the log of the conjugate base. A minus is for the conjugate base, and over the concentration of the acid that is protonated, which is a weak acid. So by looking at the equation, can you define pK? Anybody remembers? Okay. What is, okay. So if the concentration of conjugate base equal the concentration of your acid, log of 1 equals What's log of 1? Log of 1. What's log of 10? 1. What's log of 1? 0. All right. Yeah, I just like that too, but I thought you will remember it as we talk about it. All right, so log of 1 is 0. And this means pKa equals the pH of your buffer or system when in that solution you have equal concentration or equal amounts of conjugate base and the acid. When you have equal concentration, so log 1 will be 0, you have maximum buffering capacity. That's what pKa is the pH at which you have maximum buffering capacity when the dissociated concentration equal the associated. The concentration of dissociated equal the concentration of associated. So you want to know this equation, okay? Because we're going to need it for buffer calculation. All right. So here's an example, and I'll walk you through it and give you the hints to get you going. So you want to prepare a buffer that has a pH of 4.6. So usually, I mean, buffers can be any pH. Can be 4.6, can be 7, can be 9. So depending on what pH we want to choose the acid and base that will help us get and stabilize that particular pH. So it really depends on the pKa of the acid that you're using. All right, so we want to precipitate casein. We want to use a buffer at pH 4.6. And then you want the concentration of the buffer to be 1 molar. So the total concentration of the buffer to be 1 molar. Okay, let me write that down so that it makes a little bit more sense to you. Okay. Wow, that's a good workout on a Friday. All right. So, 1 molar. I want the concentration of my buffer, final concentration to be 1 molar. So, the concentration of A minus, the conjugate base, plus the concentration of the acid, you want it to be 1 mole. That's what it is. So the concentration of the base and the concentration of the acid together is 1 mole. So that's a given. That's one given. The other givens, final pH, you want it to be 4.6. That's your final pH. So in order to apply Henderson-Hasselbalch equation, you want the pKa of their acid. And in this case, it's acetic acid. So I gave you the Ka. So pKa is negative log Ka. All right, so you have the Ka. Sometimes you have a reference with, you Google, it will tell you everything you need to know about preparing that buffer. And it will spit out pKa, spit out everything for you. But sometimes you don't have that information. You go from, oh, I have the Ka. No problem. I can calculate pKa. pKa equal negative log Ka. Okay. So now you have the Ka, so you can calculate pKa, and then you apply the equation, which is equal Henderson-Hasselbalch equation, pKa, pH equals pKa plus log of A minus over the concentration of the acid. Okay, now I have two unknowns here, A minus and HA. But I have this. So let's say I substitute HA by 1 minus A minus. So HA, so now I will be solving just for X. We have two equations, two unknowns. Algebra. So if you have that given, then you can substitute HA by 1 minus A1. So then I would go pH equal pKa plus log of A minus over 1 minus A minus. From this equation, if I get the pKa, I have the pH, I will get the log of this so that I am able to get the ratio of A minus over 1 minus A minus. Can you do that? And tell me what you find out. So get the pKa, solve for the ratio, and solve for A minus. You have an answer? What is A minus, concentration of A minus is what you're solving for right now, using that way. Ah, acorns. You seen this? I have acorns. What does it mean? I'm gonna be rich? Or that means I'm a squirrel? Thank you, Gray. Appreciate that.
Hey,
What?
it means you're a cousin to Goldie and Gold.
Oh, so that means what, Goldie the Gold?
You're a cousin. Yeah.
Oh, I'm cousin to the Gold. Yes, I like Goldie. Okay. Did anybody get the final answer? Or did you get stuck somewhere, Emma? Do you have an answer for me? No? You have your calculator that allows you to do the log and negative log and all of that, right? I'm very bad with using those on my calculator, but I bet you are more savvy than I am. Did anybody get the pKa at least? Does anybody have the pKa? Yes, ma'am.
4.76.
4.76, yes. All right, so now we have the pKa. So we go 4.6 minus, what you say, 4.76. Okay. Equal the log of A minus over 1. So what you need to get from your calculator is this ratio, and then you solve for A. So this would be negative 0.16, or you can move that negative to the other side. I don't know how your calculator works, and just get what this ratio would be. You can leave the minus here depending on your calculator, or you can do 0.18 negative log the rate. Exactly. Anybody? How, do you wanna tell them how to use the calculator? What if they don't know? Do you know?
Yeah.
Alright, Alan, do you have it?
Sir, for the concentration of air, I don't know if it's right.
Alright, tell me, what did you get?
1.7.
It cannot be one, is that the ratio or the concentration? Well, but A minus cannot be 1.7, it should always be less than 1, remember?
I got an answer then.
Huh?
I might have an answer.
Okay, tell me.
0.46.
0.46, what is that? The ratio?
I don't know. 0.8.
I don't have any of those numbers, you guys.
Amazing.
Yes. 0.69, you got it. Ay. That's the ratio. Okay, so now we need log of 0.69. So how do you go from negative 0.16 equal the log? Oh, no. You got the ratio, right? Or that is what? Yes, you got the ratio without the log.
Under the power.
Yeah. No, that's correct. That's the yes. Do you want to tell them how you did it so that they can follow on the calculator?
You can also demonstrate.
I just
Go
did
up
10
to the power of the negative. It's not being.
No, they can't hear you. Listen.
10 to the power of negative 0.16.
Yeah, there you go. 10 to the power negative. I knew that. No, I didn't. I thought you guys know how to use your calculator better than me. All right, good. All right, we got that far. Now solve for A minus. You're good with that. It's algebra, right? So solve for A minus. So you have, I want to do my algebra situation, it would be 0.69 minus 0.69 into A minus. And then I bring that here, it would be 1.69 into A minus equal 0.69. Then my A minus is 0.69 divided by 1.69. You're following, right? It's just solving for x in this case. What do you get? 0.41. 0.41. Sounds right. Yeah. But you don't want to round in this case. All right, so that is the concentration of your conjugate base. So now solve for HA. So 1 minus 0.48. Oh, over there, I have that. So I'm solving here, 1 minus 0.408. I will get the concentration of the acid, which is 0.592 mole, right? Wonderful. We're not done yet. But are you all following where we got to that? Huh. Okay, are we all following to that? No, Emma, where did I lose you?
I haven't been following since the beginning.
Why did you say?
Well,
It's
you
okay,
just
try
kept
me.
going.
I kept down, you can interrupt. Tell me where, was it the application of this?
Like you just substitute things in.
Yeah,
Oh my.
so here, I just took out the HA and substituted based on that given. Over here, so that I have one unknown in my equation.
Yeah.
We go to here. Are we good till here? Substitution. Instead of HA, I put one minus AI from here. From this equation. From 1 molar.
Okay, yeah.
You got that? Okay, very good. And then by getting the, were you able to get the pKa? By applying negative log pKa? What's the pKa we found is 4.76. That's log the number I gave. Then you use your
Oh, I see.
Yeah. negative log Ka. Yeah.
Okay.
So we got that. And then now I put everything in the equation and solved for A minus. Now I have one X, yes.
If we're doing this on an exam, are you gonna give us all the equations?
What
Or we're gonna-
equation?
PK equals negative log.
That's a
Well-
simple equation. Well, oh, you know what? I'll do better. I'll give you the pKa.
Oh,
I'll give you the pKa so that you don't have to worry about negative log Ka, but you have to remember this equation. huh?
okay.
This is a good equation to remember because you will actually need it in it.
So, can you give us what is it?
What do I give you? I'll give you the pKa straight up instead of Ka.
Yeah, I think I just got confused by it. It's very clear.
Okay, so I will give you this straight up the pKa. All right, are we all good here, up to here, figuring out the concentration of the conjugate base? And then here, the concentration of the acid. Are we good through here? All right, now that we know this, how am I gonna prepare these concentrations to mix them? So I'm just gonna leave. Yep. So I have a 3 molar. My acid is 3 molar stock solution. I really want, if I want to prepare 1 liter, I need 0.592 mole. So, and I have 3 molar. So then I will do the equation of equilibrium. 3 molar times X milliliters equal the concentration I want, 0.592. And then I want to make 1 liter. That's the gift. 1 liter, not 500, correct? I want to prepare 1 liter. Okay. So I'll convert that to 1,000 ml. So how many milliliters I need from the 3 molar? 0.592 times 1,000 divided by 3 molar. So molarity cancels. Can someone tell me the that's
197.33.
197.33?
Yeah.
Oh, just 3. All right, milliliter. Very good. Now I know how much of my stock acid I want to put in a volumetric flask is that much. Now I want to calculate how much sodium acetate. For this powder, I have a powder. So then I need to calculate how much to weigh. Then here you want to remember number of moles equal mass over molecular weight. I gave you the molecular weight, and then the number of moles is this 0.408 moles per liter. We're going to prepare a liter. So this is equal, that is your conjugate base. So this is moles per liter. Okay, then the mass is what I'm looking for. And the molecular weight, I gave it to you, is 82 grams per mole. Then I solve for gram equal X grams equals 0.408 mole in my liter times the 82 grams per mole. So, sorry. So what is the amount that I need to weigh? Here I'm applying again while you calculate. I need the weight because I have a powder. So I look for the molarity that I'm after. I know the molarity that I'm after, and I have the molecular weight, so I solve for the weight. So the weight that I need is 33.5 grams in that 1 liter that I want to prepare. Okay, so now I get water. I dissolve about 500 milliliters of water. I dissolve 33 grams in it. I add 197.3 ml to that volumetric flask, and then make up the volume with water. And then I end up with 1 molar solution that has both acid and base. All right. Take a picture of it. Emma, did I lose you again somewhere? It's fine. Maybe others are lost as well. Tell me where. We'll talk. We'll talk. Anybody else would like me to do that? Okay. We can talk after class. Okay. Now, this is one way of solving it. Another way of solving it, I'll put that on canvas. Another way of solving it is the way that I really like, because for me it's easier for my brain. I prepare 1 molar solution of acetic acid and 1 molar solution of sodium acetate. And then the equation, instead of a concentration here, I would be getting milliliters volume instead of concentration, because I now have the equal molarity of the 2 solutions. I just solve for, instead of saying 1 molar equal this and that, I would just say 1000 ml is my final volume, is the A minus milliliter plus the HA milliliter. So that's 0.69 that you got here. Instead of having 1, I will just put 1000, and this will be in milliliter. The X will be in milliliter and X in. So I would just solve by amount of volume rather than a concentration. But the first step is to make the concentration 1 molar for both. For solution A, I would just say, okay, 3M, I need to prepare 1M. And let's say 1 liter of that. And then what's the XML? And I solve for that and I get the amount of the acid that I need to make up to 1 liter. So I prepared my 1 ml. For acetate buffer, the same thing. I will weigh, if I want 1 molar, I would just say 1 mole per liter equals mass in grams over molecular weight in grams per mole. So now I want to prepare 1 mole per liter, so I calculate the mass. And the molecular weight is 82. And then I take the mass, I weigh it, I put water, make it up to volume. Now I have 1 liter of 1 ml solution of the base as well. And then here, I would say X ml of A minus over 1000 minus X ml of A minus equals 0.69. So now what would be the X if you solve for X? It's kind of the same thing, but instead of 1 is 1000. So basically you end up with 592 milliliters and 408 milliliters. The only difference in this way is you unify the concentration from the beginning. You prepare 1 molar of the acid, 1 molar of the base, and just find how much milliliters from this I need to add to this to make a liter of 1 molar buffer. For me, that's the easier part, but some people just know that. Let me get molarity first, or number of moles first, and go from there. And that is, that's the answer. I'll post that up. Okay, and I'm happy to stay back a little bit after class to clarify. All right, I have 5 minutes to introduce chromatography, but before I go into that, I might not go into chromatography at all. So the lab next week, you will be preparing several reagents. You're going to be preparing a saturated salt solution that will be used in a GC lab that follows. You're going to be preparing standards, caffeine standards for an HPLC lab that follows. You're going to be preparing diluted HCl solution for cleaning glassware in your atomic absorption lab that follows. And then you will be preparing a buffer, which we will not use, but you will learn how to prepare a buffer. The pre-lab quiz is already up. One thing that you want to remember is solve your pre-lab quiz in your lab notebook. Because we're going to go over these calculations in lab. You need those for the reagents that you will be preparing. And the pre-lab quiz, you just take a picture of it and you want to upload it. Follow the prompts online on campus. Okay. That's it for that. Let's hang out for a little bit and talk casually about chromatography. All right. Chromatography. What does it mean to you when you hear the word chromatography? What does it mean? Can you define chromatography with 1 word?
Yes.
What? Gas?
Yeah.
Oh, I'm going to be super sad because there is liquid chromatography as well. But no, if you want to define the process of chromatography in 1 word, what would you say? 1 word. When you run things with chromatography, what are you really doing? Huh? Before that, that's later. You will identify, that is correct. But before you identify, the first thing you do, if you have a mixture, What are you doing before you identify the components? You run it through chromatography to do what? Separate. Simple. Very good. Well done, Colin. Okay, yes, separation. Chromatography is used to separate components in a mixture. Once they're separated, they go to a detector and then you can identify them. And you can quantify them if you have standards. But the first step is separating. If you don't separate, you don't quantify. Here's a story that I'm gonna say. If Gray remembers the story, do you remember the story that I'm gonna talk about?
One with your daughter?
Yes.
Yes.
So when my daughter was little, 11 years old to 13, that's an obnoxious age for pink. Do you agree among girls? Or those that identify as girls. So the pink is just and purple. So there is a store, there used to be a store, I don't know if it's there still at Rosedale Mall, called Justice. They got rid of it and you're sad, right? You're almost the age of my daughter. So that was the obnoxious age I was talking about. Okay, not you, my daughters. Okay. So I go to the mall. She has her friend with her that might not really like pink or purple, but she likes other stuff in the store, and my daughter is just gravitates to everything pink and purple, and everything in the store is pink and purple. And then there's me, who I don't want to do anything in that shop. So three of us walks in, and then I start zooming through everything, and then I'm out, waiting at the door. And then my daughter is like, la, 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 interacting with every single thing in the store. So she's delayed. And there's her friend, interacts a little bit and moves. So the three of us separate. We have different affinities to this store. And then, okay, her friend came out. Where's Noor? I don't know. How do we get that kid out? How do you get the kid out? How would a good mother get her out? Buy her something. Then you put as a mobile face. You put something that Solute, the daughter in this case, would like. She will hang on to it and leave the store. Otherwise, we sleep in the store. So that's chromatography. Separate different components that have different affinity to your stationary phase. And there's the one that will never come out of the column. You just put something in the mobile phase that will get them unlatched and leave the column in a reasonable amount of time, because you all want to go home after the long day of experiments. So that's chromatography. Good luck on Monday. Gary will introduce gas chromatography, and I'll be back. Well, I'll be back on Wednesday, but he still have a lecture, and then I will go back to liquid chromatography next Friday. Yay! Okay, have a great weekend. Yes, yes. Okay, if you have all of your calculations in 1 or 2 sheets, put your name on it and turn it. If not, bring them on Monday with you.
What if they're for the address?
It doesn't matter, just staple all of them together. We're not caring about organization, just want to see the work.
I'll bring like the.
You can bring Monday. You can bring it Monday.
Do we need calculation for everything also?
Yes, everything, all of your calculations put together, and then you'll get your +5. If you don't have them all, bring them on Monday.
I have like on my iPad. I could.
Yes, you can print out. You don't have to write it. Yeah. Can take a picture of it. Yeah.
They're weird.
Emma.